Hi, folks. We're moving along. This is section 2.2, matrix multiplication and linear combinations. Let's go ahead and get started. We're going to define, for matrices A and B, what we mean by the product of these matrices. And what we want is that if we multiply B times a vector, this is going to give us an answer. And then if we multiply A times that answer, we want that to be the same thing as if we multiply the product AB times X. We want these to be the same thing. So if we do the vectors, matrices B and A one at a time, that's the same thing as doing the combined matrix. So let's try this example. We're going to compute the product using the definition. This is the slow way. We're going to see a shortcut in a moment, where A is this matrix and B is this matrix. So we're going to start by saying what B times X is. So X is the matrix vector XY. And I probably shouldn't use two X's here, so I'll call this vector V instead. There we go. So B times the vector is going to be EF GH times XY. And we know that that's a linear combination using X and Y as the weights and the vectors EG and FH as the vectors. And so we end up getting the vector whose top entry is XE, I'm going to write it as EX plus FY. And the bottom entry is GX plus HY. And this is a vector. This is all one number on top and one number on the bottom. And so A times that vector is ABCD times the vector EX plus FY and GX plus HY. And that's the linear combination of the weights EX plus FY and the weight GX plus HY times the vectors AC and BD. So that is, in the top row, EX plus FY times A is AEX plus AFY plus GX plus HY times B, so that's BGX plus BHY. In the bottom row, we get CEX plus CFY plus DGX plus DHY. And if we regroup these terms, this is AE plus BG times X and AF plus BH times Y. And this is CE plus DG times X and CF plus DH times Y. And so the combined matrix AB is these coefficients right here. AE plus BG, AF plus BH, CE plus DG, and CF plus DH. Now, before I move on to the shortcut, I want to point out a couple of patterns that we see in this answer. That the values of B, E, G, and F, H appear vertically in our answers, but the values that are in A, B, and C, D appear horizontally in our answer. A and B appear across, C and D appear going across. And we can leverage that to form a shortcut that we call the column row rule. So let's take a look at how that rule works. So I want to multiply these two matrices together. This is a 2 by 2 matrix. This is a 2 by 3 matrix, but this is okay. The way we're going to do this is we're going to split A up into columns. The first matrix gets split into columns. And the second matrix will get split into rows. And then we will pair up the first column with the first row and the second column with the second row. So we're going to pair up 3, -2 with 1, 5, -1. And then we're going to pair up 1, 0 with 2, 3, 3. Then we're going to go ahead and combine this column with this row and this column with this row. So 3, -2 times 1 is 3, -2. 3, -2 times 5 is 15, -10. 3, -2 times -1 is -3, +2. And then 1, 0 times 2, 3, 3 is just going to be 2, 0 and 3, 0 and 3, 0. Reading downwards. And then we add these results together. So the top row, 3 plus 2 is 5, 15 plus 3 is 18, -3 and 3 cancel and give me 0. And then the bottom row, we're always adding 0, so we just get -2, -10, and 2. And that is our final answer. So we don't have to do the work that we did from scratch in the last example, that we can do this column row split and get the answer that way. Let's try another example. This time we have a 4 by 2 matrix and a 2 by 2 matrix. But we're going to still do the same thing. We're going to split A into columns and B into rows. So I have A gets split this way, B gets split this way. So 4, 1, 3, 0 gets paired with 3, 4. And 1, -2, 2, 6 gets paired with 1, 1. And this is going to be our answer, AB. So when I multiply 4, 1, 3, 0 times 3, I get 12, 3, 9, 0, and 16, 4, 12, 0. And when I multiply 1, -2, 2, 6 by 1, nothing changes. It's still 1, -2, 2, 6. Don't want to do that early because I have another one to multiply by. So these two combinations have taken place. We've combined this column with this row and this column by this row, and now we just need to add. So 12, 16 plus 1, 1 is 13, 17. 3, 4 plus -2, -2 is 1, 2. 9, 12 plus +2, +2 is 11, 13. and 0, 0 plus 6, 6 is 6, 6. And that finishes up that multiplication. We have a couple of theorems here. One is called the dimension rule, that if we have an M by N matrix and an N by K matrix, the answer will be an M by K matrix. The two inside entries have to match. And this is why M by N says that A has M rows and N columns. And B has N rows and K columns. But the column row rule says that we split this up into each of the columns and we split B up into each of the rows. These numbers have to match, so I have the same number of columns and rows to match up with each other. And that's why the two middle numbers have to match. But then when we're done, we will have had M rows in A and K columns in B, and the answer will be an N by K matrix. So for example, if A is a 2 by 5 matrix and B is a 5 by 7 matrix, then A times B will be a 2 by 7 matrix. The inside numbers cancel, the outside numbers give me the size of the answer. The other theorem we have in the book, it's called proposition 2.2.4. If I have a matrix that has vectors for these columns, v1 through vn, and then x is a vector that contains the weights x1 through xn, then these three statements all mean the same thing. They're just three different ways of saying the same idea. X is a solution to the vector equation ax equals b. Or we can say that B is a linear combination of the columns of A using x1 through xn as the weights. Or we can also say that the components of X solve the system of equations whose augmented matrix has these vectors from A on the left side and whose augmented column is the vector B. All of these say the same thing. One says it using the language of system of equations. One says it using the language of linear combinations. They all mean the same thing. All right. So this next definition is pretty simple, I think. When we transpose a matrix, the transpose and the little capital T at the top is an indication that we're transposing a matrix. We're not doing any math to the matrix. We're just rearranging the layout so that the rows of the matrix are now the columns and the columns are now the rows. Here's what I mean. So this matrix A right now is a 4 by 2 matrix with these entries in it right here. We've seen this matrix already. We want to write the transpose. So I'm going to change the layout of the matrix but not do any math to it so that the column 4130 is now a row and the column 1 negative 226, that's also a row. And now the matrix is a 2 by 4 matrix. We're not changing the information, the data in the matrix, we're just changing the way it's laid out. One thing that we will make use of way in the future when we get to chapter 6 is that when we combine A and its transpose either by addition or by multiplication, we always get a symmetric matrix. So let's show this. So matrix A is 1, 2, 3, 4. So then A plus AT will be 1, 2, 3, 4 plus, and then the transpose is the column 1, 3 becomes the row 1, 3. The column 2, 4 becomes the row 2, 4. And so if we're just adding, the top row becomes 2, 5, and the bottom row becomes 5, 8. And this is symmetric about the main diagonal. We have a 5 on one side, and we have a 5 on the other side to match. That's symmetry. If we multiply A times AT, we are multiplying, so we use the column row rule. So we're going to combine the column 1, 3 and the row 1, 3, and then we'll combine the column 2, 4 and the row 2, 4. So 1, 3 times 1 is 1, 3. 1, 3 times 3 is 3, 9. 2, 4 times 2 is 4, 8. 2, 4 times 4 is, I need to make room for this, 2, 4 times 4 is 8, 16. And when we add them together, we get 1 and 4 is 5, 3 and 8 is 11, 3 and 8 is 11 again, and 9 and 16 is 25. And once again, this matrix is symmetric across the diagonal. The 11 on one side has an 11 across the mirror to the other side. All right, let's move on. Just a couple of warnings about how multiplication works. Multiplication of matrices is different from the way that we multiply numbers. With numbers, the order does not matter. 2 times 5 is equal to 5 times 2. That works for numbers. But it's just usually not the case that it works for matrices. A times B does not equal B times A, except in special cases. For example, if one matrix is all zeros, for example. So let's try this. If we multiply A times B, we get the column 2, 0 paired with the row 1, 0, and we get the column 1, 3 paired with the row 1, 2, and so that's going to be 2, 0 times 1, 0 will be 2, 0, 0, 0. 1, 3 paired with 1, 2 is going to be 1, 3, 2, 6. And when we add them together, our answer is 3, 2, 3, 6. But if we multiply B times A, let me write that down correctly, 2, 1, 0, 3, then we're pairing, our pairs are different. We're pairing 1, 1 as a column with 2, 1 as a row, and we're pairing 0, 2 as a column with 0, 3 as a row. And that's 2, 2, 1, 1 plus 0, 0, 0, 6. And that's the matrix 2, 1, 2, 8. 2, 1, 2, 7. And these matrices are not equal to each other. And so with matrices, the order does make a difference. We cannot just switch the order the same way we can with numbers. There's even a more basic reason. If A is a 4 by 6 matrix and B is a 6 by 4 matrix, then for AB, the inside numbers cancel, and AB is 4 by 4. But BA, the inside numbers cancel, and BA is 6 by 6. By the dimension rule. In this case, A and B are not even the same size, so they definitely cannot be equal. Here's another law that doesn't quite work for matrices the way it works for numbers. For numbers, if we have the same coefficient on two sides, like 5x equals 5y, we can cancel the 5's and say that x equals y. But with matrices, if I have A times B equals A times C, I can't automatically cancel the matrices A and say that B is equal to C. Can't cancel the A's. Let's demonstrate why that doesn't work. I have three matrices here, A, B, and C. If I multiply A times B, we get 2, -3, -4, 6, multiplied by 8, 4, 5, 5. Columns and rows, so that's 2, -4, 8, 4, plus -3, 6, 5, 5. So let's see, 2 -4 times 8 is 16 -32. 2 -4 times 4 is 8 -16. 3 -6 times 5, 5 is -15, 30. 3 -6 times 5, 5 is also -15, 30. And when I add them together, 16 minus 15 is 1. 8 minus 15 is -7. -32 plus 30 is -2. And -16 plus 30 is 14. Let's see what happens when we multiply A times C. This time we're multiplying by 5, -2, 3, 1. So again, columns and rows. This time we'll be multiplying 2 -4 times 5, -2. And -3, 6 times 3, 1. So the first matrix will be 2 times 5 is 10, -4 times 5 is -20, 2 times -2 is -4, -4 times -2 is +8. -3, 6 times 3 is -9 and 18. -3, 6 times 1 is -3 and 6. And when we add these together, 10 and -9 is 1. -4 and -3 is -7. -20 and 18 is -2. And 8 plus 6 is 14. We get the same total, but we get it in two different ways. And so A times B gives me exactly the same total as A times C. That's correct, but it's not true that B is equal to C. B and C are two different matrices. And so I can't automatically cancel the A's. We just have engineered two different matrices that manage to somehow give us the same total. So cancellation does not work with matrices. And the third rule that doesn't apply is that if we multiply two scalars, if a times b is equal to 0, then I know that either a is 0 or b is equal to 0. But with matrices, I can have a matrix that's not 0 and a matrix that's not 0, but are engineered in such a way that when we combine them, the total turns out to be 0. The product of two non-zero matrices can be 0. So with that in mind, can we decide if this is a true statement or a false statement? Well, if we FOIL, then we get first times first is a times a. Then outer is a times b. And then inner is b times a. And then last is b times b. And a times a is definitely a squared, and b times b is definitely b squared. I actually went ahead and wrote that as b squared. I'll fix that. But remember that the order matters. AB and BA can be different. And so I can't automatically combine them and make 2AB. So these do not automatically combine. And so this rule works for numbers, but it doesn't work for matrices. Let's try one more, and then we'll wrap up. Can we do the same thing with the difference of matrices? Well, again, foiling, this gives me a squared, or a times a. Outer is a times minus b. Inner is b times a. And then last is b times minus b. And this is a squared, and this is b squared, but these could be different, and these don't cancel. May not cancel with each other. And so we can't say that the right side automatically just equals a squared minus b squared. This is another factorization law that works for numbers, doesn't work for matrices. So unfortunately, we can't always get the same nice algebraic rules for matrices that we can for numbers. We just have to be careful about this weird rule about not being able to switch the order of matrices. All right, we're going to wrap up. Have a great weekend. I will see you in class.